So how does the interaction between Plutus and staking work? We have talked about script purposes. If you recall the script context that our Plutus scripts always receive as one of the arguments, contains a field of type script purpose. And during this lecture so far, we have only looked at the first two purposes. The arguably most important one is spending TX outref. So when we are spending a UTXO sitting at a script address, this UTXO is identified by its TX out reference, then the corresponding Plutus script is executed and it receives the datum of the UTXO we want to spend, the redeemer, and the script context. And then we can put arbitrary logic in the script to determine whether spending this UTXO is valid. Then we had the minting script purpose, which is for minting and burning native tokens. So whenever a transaction mints or burns a token, then the minting script corresponding to the currency symbol of the token is executed. And again, we can use arbitrary logic. The script receives a redeemer and the script context, and we can determine whether minting or burning for this transaction is valid or not. But we haven't talked about rewarding and certifying it, and those two are related to Plutus and staking. So as I briefly mentioned before, instead of using a public-private key pair to create a stake address, we can instead use a Plutus script. And then the hash of that Plutus script will give a stake address, a script stake address. And where, as we saw in the previous example, if I want to withdraw my rewards, for example, for a normal stake address, I have to, as witness that I'm allowed to do that, provide the signing key for this stake address. So if I use a script stake address, then instead the corresponding script will be executed. It will receive the redeemer and the script context. And again, I can use arbitrary logic to determine whether this transaction is allowed to actually withdraw those rewards. Similarly, certifying decert. So there are various certifications that I can attach to a transaction. In particular, important for staking are registration, delegation, and deregistration certificates. So if I newly create a stake address, I first have to register it by creating a transaction that contains a registration certificate for this stake address. Then if I want to delegate to a pool or change an existing validation, I have to use a transaction that contains a delegation certificate, and that certificate then contains the pool I want to delegate to. And finally, I can also unregister a stake address again and get the original deposit back that I had to pay when I registered the stake address. So for those, then if I do a delegation, for example, then again the corresponding script will be executed and can contain arbitrary logic to determine whether this delegation, for example, is legal or not. So I want to concentrate on the rewarding purpose in this lecture. So if we look at the TX info type again, then we have covered some of those fields in previous lectures. So we have talked about the inputs, the outputs, the mint field, the valid range, which allows us to reason about time, the signatures that are required, and staking related are these two. The TX-info decert, a list of certificates that are attached to the transaction, and this TX-info withdrawal, which is a map from staking credential to integer. So we want to concentrate on this field in this lecture as an example to see how Plutus influences withdrawal. The way it works is, so when the transaction withdraws rewards, then in this map, the key is staking address. So you can withdraw from several staking addresses in one transaction. So therefore it's a map, not just a pair. So there can be several such pairs. So the key is the staking credential, which can be given by a key pair, which is the normal case, or which is the focus of this lecture, by a Plutus script or the hash of a Plutus script. And then the integer, the value, denotes how much we withdraw, how many Loveless. And when this staking credential is given by a Plutus script, then when we try to do a non-zero withdrawal, the corresponding Plutus script will be executed. And again, as before, for validators and for minting, if this script runs without error, then the withdrawal is okay. And if it produces an error, then the transaction becomes invalid. I provided an example of a Plutus staking script in this week's code folder, and it's named staking. And I don't think it's a very realistic example, but nevertheless, so the idea is that we want to define a stake validator that controls withdrawals of rewards, and it is parameterized by an address. And then the idea is it only allows withdrawals from the corresponding staking credential given by the script if at least half of the withdrawn rewards go to the specified address. So how do we do this? So first of all, I, again, as always, use the typed version. So the actual thing that runs will be an untyped version where everything is built in data and where the return type is unit and failure is indicated by producing error. But as always, we use proper Haskell types and the return type of bool and then later convert into this untyped version. So let's first look at the type version. So the first argument here, the address is a parameter of the script. So it's parameterized by this address. The next one is the redeemer. We don't have a datum. It's similar to minting scripts. Remember, minting scripts also only take redeemer in script context, and it's the same here. So no datum, this is the redeemer, but I don't need the redeemer, so I just use unit. And as always, we get the script context. So what do? I first look at the purpose. And as we have seen, that could be certifying if it involves certificate, delegation, for example, or rewarding. And this example is only about withdrawal of rewards. So if it's about certificates, I just say it's okay. So you can do whatever you like with this staking credential given by this script. If, however, it's rewarding, then I check whether half of the withdrawn reward is given to this specified address. So I have a helper function defined below, paid to address, which will give me the amount of Loveless sent to that specified address. And I check that twice that amount is greater or equal to the withdrawn amount. And that, of course, is equivalent to what I said earlier, that at least half of the withdrawn amount is paid to this address. So I have two helper functions. One is amount. So how do I do that? Remember, we looked at the txinfo withdrawal field, which was this map from staking credentials to integers. And I know the staking credential that's given by the script purpose. So that is the staking credential given by this script. So that's a bit circular again, but the same happens for minting policies, where we also sometimes want to talk about the currency symbol or minting policy we are just defining. And this is similar here. So we are just defining this staking credential, but it's given to us in this script purpose, in the withdrawal purpose. So this credential is the one we are just defining here. So I have this map of withdrawals, and I just look up the credential, our credential, this credential. And if it's not in the map, then it's an error, but that can't really happen because the script will only run if we only get to this point if we do a withdrawal for this credential. So I will find this integer, and that's the amount I return. So this takes care of the right-hand side. So this is now the number of Loveless we are withdrawing as rewards. And now I have to figure out how much I'm paying to this address. That's the parameter to the script. And this is simple, so I just loop over all the outputs of the transaction. And then for each of these outputs, I check whether it goes to the address in question, the one I'm interested in. And I have this accumulator. So the n sums all the amounts. I mean, I do this loop because there could be several outputs to this address. And I'm just interested in the total amount, in the sum. So if it doesn't go to the address, the sum doesn't change. But if it does go to the right address, I just extract from the output value using the function value of that takes currency symbol and token name. I apply that to the ADA symbol and the ADA token name, and thus get the amount of Loveless that goes to this address in this output, and I sum over all of them. So this gives me this part here. And then I check the condition, and if it's not fulfilled, then I just trace this error message, insufficient reward sharing. And that's basically it. Now it's just boilerplate. So first I have to convert that into the untyped version. And similar to before in our utilities package, I added that in the Plutus TX part. And actually it's identical to the minting policy wrapping, because I mean, there we have the same signature. It's also some arbitrary redeemer type and then script context and bool, and that has to be converted to built-in data unit, and this is exactly the same. And I just implement it like that. I just didn't want to use wrap policy directly because then the name is misleading. I mean, I could have renamed this wrap policy into wrap policy or stake validator, but I thought it was easier like this. So that's that. So given our typed stake validator, we can use this wrap stake validator function to turn it into an untyped stake validator. And then we use the usual template Haskell magic, except this time we use this make stake validator script, which is defined in the Plutus package. And again, we have to apply the parameter. So I explained that before, how parameterized scripts work. So I have to use this apply code and then lift the address into Plutus code. So this gives me for each address a corresponding stake validator. Now to actually use that from the Cardano CLI, for example, I must have a way to actually execute that and serialize the resulting stake validator to disk. So there, first of all, in serialize, I already had serializations for normal validators and for policies, and now I just added one for stake validators here. So that's exactly the same. And finally, there is a little annoyance. In order to actually apply this, we need a Plutus address. But normally our addresses are in form of a string in a bech32 representation normally. For example, if we use this private testnet setup, then we have the addresses of the users. At the moment, there's only one user in the form of such a string. And it's not completely trivial, unfortunately, to take such a string and convert it into a Plutus address. And therefore, I have this conversion module that we have used before, and I added code here at the bottom to pass a string into a Plutus address, or to try and pass a string into a Plutus address. So that's a bit messy because there are all sorts of cases to consider, but this basically does it. And that's one pain point with Plutus, in my opinion, that there are these different versions of the various types. For example, address. There are addresses defined in the Cardano API, which is what the Cardano CLI uses under the hood. That in turn uses more fundamental address types from the Cardano Ledger modules, and Plutus does its own thing. And for example, now if you actually want to use it, you have to convert between those. So what I do here, first I, given the string, I deserialize it into a Cardano API address. And then there are various cases. So for example, that can already fail, or it can be a Byron era address, in which case it also fails because Plutus only deals with Shelley era addresses. And if it's a Shelley era address, then I have this payment part and the staking part. And I have to handle them separately. So that's these two helper functions here. So this converts the payment part to Plutus, and this converts the staking part. And then there are, again, several cases. So in the payment part, it can be a script address or a pub key address. And in the staking part, it can not be there, in which case it's a address that doesn't use staking, or it can again be script or pub key. And then there is this additional case that I have never seen used in practice, which is a so-called pointer credential, where you can point to a specific point on the chain. I mean, I've just implemented it for completeness sake, but we won't use that. So we are just interested in this base case. Anyway, so this is now available in the conversion module, and you can use it to use string representation of an address and convert it from Plutus address. And then together with the serialization I defined, we have this safe stake validator that takes the address as a string and then tries to pass it as a Plutus address using this conversion function. And if that fails, I throw an exception. And if it succeeds, I use my serialization function to write the resulting validator to this file in the assets folder of this week's code. And in the next part, we'll actually try this for a specific address and see whether it works. And this is already everything we need to try out staking with Plutus. So a stake address that's not given by a key pair, but instead by code. And in this example, as I said, it enforces this logic that whenever you try to withdraw rewards from this stake address, you have to give at least half of the rewards to the address that's the parameter.